Brandon, can you hear me okay?
Yes, I can hear you.
Okay. I gotta get this.
It says there's only two. Oh, there's only two people in here.
There are more coming. There was a problem. Hopefully everybody can get in.
Here they come.
Yeah, I know. The problem is the waiting room. I don't want that chime on. You can hear me okay though?
Yes, sir.
Okay, give it a second. There's some problems. Can you see how many people are there? Or not?
14.
It says 14.
All right. Just keep an eye. There was a problem with this Zoom meeting thing. There were like 2 meetings up. Did you get your quizzes back? Or your quiz results, pardon me? You did? Okay. And y'all can hear me and see
Wait,
me?
Dr. Baginski, I think there's only 19 people here. I think they're all in another meeting.
Yeah, I don't know exactly what's going on. The meeting started before I sent out the invite. I don't know how that happened. Just hang on for 1 second. There should be.
My roommate's on the other meeting. You want me to? I'll say something to. You want me to say something to those people?
Yeah. By the way, can you see me on the other one?
No.
Okay. Good. I don't know what's going on. I know. Frankly, I sent the invite for this meeting. Now I don't know if somebody.
So I think everyone needs to get on the link that you emailed.
Is that you, Kendall? That's talking?
Yes, it's me.
Could you please invite or tell everybody that this is the meeting that there should be an invite there on your email, and you said you got one?
Let me look.
See, I sent one, and before I looked, and somehow there's another meeting, a 3810 meeting. I'm thinking, well, it ain't me. I don't know sometimes how this happens. What time did you get on?
I got on right at 1:03 when you sent the email link.
Well, I was trying to get on here, and the thing was just spinning and spinning and spinning. I mean, there was I frankly don't know what happened.
Okay, so my roommate's Maddie. Let me tell the other people sitting on the other meeting to come in this one.
Yeah, tell them there's been a problem. Tell them to check their email for the link. Thank you.
Okay, I think everyone's coming, Dr. Baginski. They're all getting off that one.
I'm sorry it happened. I don't know how it happened, frankly, though. That's even worse. I mean, I didn't send the invite. I didn't do anything, and I couldn't get this one up for some reason. Are you seeing a shared screen right now or not?
Yes.
Okay, thank you. How many we got on there now? Because it's absolutely eclipsed on mine.
We're at 58 now.
Oh, that's excellent. There's more coming. Good.
That's better than 20.
That's right. It's better than 20. Just give it a second. I think we'll have a full house in no time, I hope. And this, I have to admit this, I don't know exactly what happened, because when I got on here to send out the invite and stuff, there was already a meeting in progress, and I'm looking, wait, and I tried to join that one and I couldn't join it. And it's my meeting. How can I not join it? But I couldn't. So I don't have any idea how that happened. Give me 1 second. I'll be right back. All right. Let me make sure this is working. Can everybody hear me okay?
Yes.
Okay. And how many people do we have? I'm looking at only 60.
Yeah, 60.
There should be more.
More might be coming because I was also in the other group meet. There was 2 links that was on the Zoom, so I
Yeah,
joined.
it's Caleb. There's a person, Caleb said the meeting you posted at Canvas. I didn't post anything in Canvas.
There was 2 on Canvas actually. There was one on the Zoom thing happening today. There was one at 1 p.m. and one for 2. I clicked on the first link and there were some people there. They left there to come to this one. So
That's bizarre. I mean, I didn't do anything. Usually I have to start, create a link and send it out. And I was trying, there was already a meeting in progress and I tried to get on it and I couldn't. But I didn't start that meeting. If somebody did, well, they did. I don't know how that happened. But you should be seeing a screen right now where there's document cameras coming up.
We're seeing a screen with the troubleshooting compatibility thing.
That's the one. That's the one. Thank you. All right. Hopefully it's coming up. Oh, not this thing with malware bites again. Let me just do this. I have no idea why that does it, but it does. All right, what I'm gonna do, this thing should come up. I hope it comes up. This is usually up before I start the meeting. Come on. So I hope this does it here. Oh my gosh, now what? So I'm apologizing to this. This is unexpected. I don't see anything that could mess it up. try one last time. Everything's plugged in. It was working fine. Oh, I think it's coming now. Thank God. I hope. Finally. Sorry, guys. This time. All right, good. At least maybe change the size of this thing. Good. All right, back to where we should have been 20 minutes ago. I want to get through this power business. We went through average power, and we were talking about RMS in general, RMS power. Now, today I want to just mention a few things, and I'll take your questions and problems in 1 second. When we talk about RMS for anything that's sinusoidally or cosinusoidally varying, this is what it indicates, and I want to go through this just to make sure everybody's clear about this. So if we have a system where we have plus the minus voltage, V of t is equal to some Vm here, cosine of omega t, as such, that's just a voltage with a magnitude Vm, and we have a load here, Z, all right? Now I'm putting Z as some magnitude and some impedance, so leave that as magnitude of Z at some angle, theta Z. Now this is what happens, and it happens often in engineering. This is in the time domain, and this is actually in the phasor domain. It's a magnitude at an angle. Do y'all follow me in this class? It assumes that you're being excited by a constant frequency. By constant frequency, I mean either a cosine or a sinusoidally varying waveform at a frequency omega. Can you all see this okay, by the way?
Yes. Could you
Okay.
co-host Jessica and I?
Yeah, and I appreciate you reminding me. If I can find her. Okay, everyone? Jessica, I think you're
Yes.
co-host.
Yeah, I
Eh,
can.
All
Yeah.
right. Go ahead. All right, back to this. When we have this waveform right here, the actual peak value, the way we've been doing it, is just Vm at an angle of 0 degrees here, because there is no any angle inside that argument of the cosine. Are you with me, class?
Yes.
This is the peak value, Vm. In general, it would give rise to a current I right here. The current I would be given as Vm at an angle of 0 degrees divided by magnitude of Z, whatever that impedance is, at angle theta Z. Or we could write it as this. We could say this is really equal to, I could be equal to Vm over magnitude of Z. That would be the magnitude right there. And the phase angle would be minus theta Z. I'm doing it for a reason. Y'all follow me? Here, when we look at this, this is all in terms of the peak value of the actual voltage and the current. We can easily go ahead and take this information right here that I circled and call that Im. We could say Im is at an angle minus theta Z. That could also be indicated as I. In some of the notes you're going to see in the book that you purchased, you'll see a little tilde over the top of that. The tilde just indicates a phasor. Now, I don't do that for a reason. This information alone tells me it can only be a phasor. A magnitude and an angle indicates it can only be a phasor. It's at a given frequency that isn't included in this information, but it is included here. Everybody with me so far? We've covered this a couple of times already. Now, when we have this, if I wanted the time domain form of I would say I of t, and this would be I of t here, right? We'd be going in that direction. I of t would be equal to the magnitude here, Im, right? And it would be at cosine of omega t minus theta z.
Are you writing that as a lowercase I?
Yeah, and the only reason I'm doing lowercase is because the book uses lowercase I to indicate time domain, uppercase I to indicate phasor domain. Both your book and the problems that I've provided. Do you follow me, everyone?
You're a little zoomed out. It's kind of,
I think it's because I used a different resolution for the camera. Can you see it now?
yeah.
Okay. This is a recap. Here, Z can be anything, magnitude and phase. It could be a real number with an imaginary number. We would get a magnitude and a phase angle. Here, we could have provided a phase angle. I chose not to. Now, all these values, both Im here and Vm, are in peak value, or they are in the magnitude. If we wanted the RMS value, and this is important, we would say that VRMS is equal to the magnitude over the square root here of 2 for VRMS, and likewise IRMS would be equal to I magnitude over the square root of 2. I did this last time, I believe. You all follow me? Everybody.
Yes.
Again, this is recap, but it's important because I gave you specific problems, didn't I, about RMS. Now, this RMS is related to this cosinusoidal variation or sinusoidal variation, periodicity. We call it steady state. When we look at power in general, the average power, here this would be power, but it would be average power. Average power, PAV, that's equal to 1/2 Vm Im times the cosine of theta V minus theta I. This is the one where I made a mistake in class, if you recall. And whoever corrected me, I thank you again. Here, Vm and Im are the magnitudes. Everybody follow me on that? If you can turn on your cameras, I appreciate it, but if you don't want to, I understand that. Now, this is also equal to, now take a look here. Since VRMS, or I should say Vm is equal to the square root of 2 VRMS, and I magnitude is square root of 2 IRMS, if we would replace Im and Vm here with the IRS values times square root of 2, we'd end up getting VRMS times IRMS times the cosine of theta V minus theta I. Both of these are average power. Both of these equations contain the identical amount of information. The difference is that here I've used the RMS components of V and I, and here I use the magnitude. Now, I don't know who reminded me that I made a mistake when I forgot the 1/2. And I apologize again for this, but this is the reason I'm doing this is because almost all the calculations we do when we talk about power assume an RMS voltage or an RMS current. Does everybody follow me on that? I'll say it again. Almost all the voltage and current problems that you'll get will state an RMS value of voltage and an RMS value of current. Let me say one other thing. When you think about what's in your house, you have about 120 volts RMS or 117, if you're exact, volts RMS out of your wall for an extension. Correct, class? And I appreciate you turning your cameras on. That actually helps me a lot. You all know what I'm talking about, everybody?
Yeah.
Heads waving. All right, now the peak value on that would be the square root of 2 times that RMS value. Do you understand? So your actual cosine waveforms, you put a meter in the wall and you look at the peak value with your meter, you'll get the square root of 2, which is, you know, when you take about 1.414 something times the 120. It'll go about 160, 170, somewhere in there. And that will be the peak value. But the actual RMS value will be that divided by the square root of 2, or about 117. I want to make sure you got that. Now, every single engineer is going to have to know that at some point in your life. If you're doing any kind of engineering work that involves the wall voltage, just keep that in mind. One other thing, I didn't say this, maybe I did say it last time. What is the frequency of the circuitry here in America of all power delivered? The frequency, anyone?
60?
60 hertz. It means there are 60 cycles per second, 360-degree cycles. Does anybody know what it is in Europe? Anyone?
50?
It is 50, and it has a higher voltage. I think it's 205, something like that. It's higher. Has anybody lived in Europe at all for any length of time or been to Europe? Jessica, surely you know. All right, is it 205, the voltage there, or not? But that's the RMS voltage. Remember this if you ever do work engineering stuff for Europe. They have a different voltage standard, a different frequency, and a different average or RMS value. It's very important if you're designing equipment to know this. One last thing, if any of you are in the military, you have to travel there with your stereo equipment or anything that plugs in a TV, you have to get an adapter because you'll blow up things. It happens all the time in the US military where people will destroy the power supply in their stereo receivers and stuff like this. And it's been a long time since I've destroyed anything like that, but it happens all the time. Now, that said, when we get into this, how do we use this information to actually calculate problems? Remember before I told you that this was the calculation you would look at when you did power absorption or power supplied, right? Both the voltage and current were, current was going into the positive terminal that you declared for the voltage measurement, correct, class?
Yes.
Same exact thing, only the square root of 2 is gone if we're looking at RMS. I really don't care to do an RMS calculation unless you want me to. I did one. Personally, I will not test you on applying what VRMS is to a waveform. I gave you problems about this to get you acquainted with it. That's the only reason I did that. You follow me? So you'll be acquainted with it. One last thing I'm going to say, this is so you won't get deceived. If you ever go buy stereo equipment, there are about 3 or 4 measures, high fidelity sound replication equipment. One is the power. Always look at the average power, never peak power. You can get peak power that'll be 300-400 watts, where the average power may only be 20 watts. All right. But remember, you will always look at the peak or at the average power that's delivered. In the peak power, you just don't take that and divide by square root of 2. There are tricks that the manufacturers use to sell equipment. The second thing is you look for distortion. There are 2 types of a distortion. One is total harmonic distortion. The other is intermodulation distortion. The lower those values, the better. Look on the web for some measures of standards as what is good. You will be buying, if you haven't already, high fidelity equipment at some point for your home entertainment system. Remember what I told you. You heard it here. Now, back to power and how you actually go about using this to solve things. We don't use this equation per se, but we use the equation I pointed the arrow at with some modifications. We will say the average power will be equal to VRMS times IRMS. And then they'll put the term PF, which is power factor. So write this down, the power factor. The symbol for that is PF, and that is the cosine of theta V minus theta I. You can look in your book and look up power factor. It is in there. It's also everywhere. It's a standard. Remember this. This is important. Now here's the problem. If I just tell you what the power factor is, there's an ambiguity, and here's why. How many know the cosine of x is equal to the cosine of minus x? And x can be any numerical value for angle. How many know that? That is one of the properties of an even function. So just giving the value of the power factor doesn't necessarily uniquely identify if the voltage is leading the current, if the voltage minus the current is positive, or if the voltage minus the current is negative. More information is needed. Do you all follow me on that? Simply saying the cosine, or really the power factor is 0.8, doesn't tell me if theta V minus theta I is positive or negative. Does everybody understand that?
Mhm.
There is not enough information to make that determination. So what they do is use the term lead and lag. Y'all follow me? Now, when they talk about a leading power factor, it means the current, or I, leads the voltage. A lagging power factor means the voltage leads the current. I want to give you some specific examples of this. By the way, well, no, I'm going to just stop there. Leading, I leads V. Lagging, I a V leads I, or really the way that they would say this is I lags right there, V. You all follow me? Now
I'm not
here's
sure.
one.
Like you might just be about to get to this, but I don't quite understand what you mean by leading and lagging.
Good point. You're about to find out. Before you do, let me just put it this way. There's a term that I think I learned this in high school. I had an electronics course. They use the term Eli the Iceman. Just write it down. Eli the Iceman. All right. You're going to laugh at how simple this is, but I do this for a reason. I'm taught this. If anybody here has a radio telephone license, any kind of a FCC license where you're a ham radio operator, you learn this as well. The symbol for an inductor is L, is it not, class? Right? Here's something to keep in mind. The symbol E in the British system and in the standard, if you're a 2-year degree in electronics, you get this. E is the symbol for voltage. So Eli, well, L is an inductor. In an inductor, the voltage leads the current. In a capacitor, the current leads the actual voltage. These are things that you learn. And let me go through and give you a specific example, because everybody's thinking, what does he mean by lead and lag? Technically, I could draw this for you in a time domain. It's easier to show it to you in the phasor domain. Okay. All right, I'm going to go with the capacitor or for the inductor first. So if I have a voltage source right here, my voltage source is just going to be Vm at an angle of 0 degrees. I'm going to make it as easy as possible. Now, an inductor has an impedance right here of J something. Do you agree with that? I'm just going to call this impedance Jx, where X is a scalar positive value. That's the impedance, and the units would be ohms. It gives rise to a current here, I, that would be equal to the voltage divided by the impedance, or it would be Vm at an angle of 0 degrees divided by this, right? Now, isn't Jx ohms, isn't that really magnitude of X at an angle of 90 degrees? If I wanted to talk about degrees and not radians, do you agree with me? Take a careful look. If I had Jx, J10, that's really 10 at an angle of 90 degrees or at pi over 2 radians. Do you all agree with that? I want you to take a good look at this. So if I take this divided by the magnitude of X at an angle of 90 degrees, then my value of I right here is really equal to what? Magnitude of Vm over magnitude of X. That's a scalar. And the angle would be 0, minus 90, or minus 90 degrees, right? Do you agree with me? Now, this is a current. The voltage was Vm at 0 degrees. Do you see for an inductor, the voltage leads the current by 90 degrees. Compare these two. Voltage is at 0 degrees. If it's leading by 90, it means the current has got to be less that angle, less 90 or minus 90. Do you all see this? How many do? Okay. Brantley, can you see this or not? I mean, can you see that's a minus 90 or not?
I can.
All right, can you see this is 0?
Yes.
That's a voltage, right? Applied voltage. The current will always be 90 degrees behind that angle for an inductor. Do you follow me?
Okay.
And that is called, right here, a lagging power factor. So this is a lagging. Now I'm going to just flip it over here, try to make sure. I said lagging, V leads I, right? Right? voltage leads current by 90 degrees. It's called a lagging power factor because the power factor always deals with the position of the current with respect to the voltage. The term lag means the angle is less than whatever the angle is here. Let me give you another example. I'm choosing ones that are, I think, very apparent to you. If this was not 0 degrees, suppose this was 90 degrees for the voltage, same exact problem. What would the angle of the current be? If
Did you
the
say that again? I was.
Yeah, if the voltage is, say it's Vm at an angle of 90 degrees, say it's lagging power factor by 90 degrees, what would Im be? Just Im at an angle of
0?
0, right? Suppose I had Vm at an angle of 180 degrees. Im at an angle of
90.
90. You get the idea. That's a lagging power factor, lagging by 90 degrees, specifically for an inductor. Do you follow me, everyone? It doesn't have to be by 90. It can be by anything. But if it's a lagging power factor, you would take the inverse cosine of the angle, and I'm going to do this for you. I'm just trying to give you the overview. I would take the inverse cosine of the angle, and I'll get an angle, whatever it is. It might be 10 degrees, 30 degrees, something like that. Now, if it's a lagging power factor, whatever the angle is on the voltage, I would subtract the actual angle associated with the inverse cosine from the angle associated with the voltage to get the angle on the current. We'll be doing that. Do you follow me? How many see that or understand what I'm saying? It's very clear when we do this. Now, if it was a leading power factor, and that's this thing right here, ice in a capacitor, the current leads the voltage by exactly 90. So if we have a capacitor right here, and I like to do this too, I'm going to put the same exact situation here, Vm at an angle of 0 degrees. The capacitor has a negative J sense to its impedance, so it'd be minus Jx, right? That's the ohms, right, class? It's really 1 over j omega c, but it'd be minus Jx, and the units would be ohms, or it would be magnitude of x at an angle of minus 90 degrees. Do you all agree with that? I know it's going to seem too simple to some of you. Bear with me. This is for everybody's benefit. Now, if we want this current, the phasor current here, remember that's a capacitor, right? We would say this phasor current would have a value of Vm at 0 degrees divided by magnitude of x at minus 90 degrees. Correct, class? I'm just drawing this to show this clearly. Okay? And when we take a look at that, we would have a magnitude of Vm divided by magnitude of x, right? What would the angle be, class? 0 minus a minus 90 or plus 90 degrees. Agreed? Now, you see here that the current itself, if I look at the voltage, it's Vm at 0 degrees, but the current would have a value of Vm over x as its magnitude, but it would be a plus 90. This is leading by 90 degrees. Can you all follow me on this? I'm showing you the differences between leading and lagging with the extreme example of just a capacitor or just an inductor. By the way, what would the average power be absorbed by either the capacitor or the inductor? Average power, anyone?
0.
It's 0. I'm restating this. You can't. Repetition is very good at helping people retain information. Now, those things I've showed you are extreme, but they'll help you, especially Eli the Iceman. I'll help you remember this stuff. Now, when I go ahead and I take a look at typical problems that we can work with the term power factor and apply this. I want to go ahead and show you. First, I'm going to say this. I want to just state this explicitly so people don't get confused. I'm going to say average power is equal to VRMS times IRMS times the power factor, PF, and the power factor is equal to cosine of theta V minus theta I. Okay? I want you to note this. This is average power. Average power. The units of this are watts. Please listen to me. A very typical problem is shown here. I'm going to give you more information in your PowerPoints to reference. I'm going to go ahead and give you problems, but I want to work problems to show you exactly how this applies to problems. If this is the problem here, I say that I have an average power of 88 kilowatts. Do you follow me on this?
We can't see that.
Ay, ay, ay. Thank you very much. Well, the real problem is the resolution here. I don't think I can focus that either. That's about as good as it gets. Can you make that out?
That's a little bit better.
All right. They're saying there's 480 volts RMS. I hope you can see this, and I'll deal with this resolution problem in a second, but not now during the lecture. They give you 88 kW and they give you this power factor and they want this current. You all follow me? Now listen, they say it's lagging too, all right? Before I show you the solution, just listen. We know that the average power, that PL is average power, it's kW, so it's 88 times 10 to the third. That's equal to VRMS, which is given, is it not, class? Right? They give that as 480 between here and here. Do you see this?
Yeah.
Times IRMS, which is not given. Do you all see this, class? They give you the voltage and they don't give you the current, but they give you 88 kW, that's on the other side, and they give you the power factor. So they give you 3 of the 4 to solve this equation. They give you this, they give you this, and they give you this, and they want IRMS. Do you all see that? Therefore, we can get IRMS shown here. Now, they use a capital PF. I don't. They just take the total power, which is 88 kW, divided by the power factor, which is 0.9, and then they divide it by the RMS voltage. Can everybody see this?
Yeah.
That gives you the magnitude of the current, but it does not give you the angle. Here they have more information. Now I know the magnitude of the current. Please listen to this. Are you with me? I know the magnitude of the current. That means I also know the power that's actually lost here in that 0.08 ohms, because now I know, remember we have an RMS current. So the power lost here would be the IRMS current squared times the resistance of 0.08. Can everybody see this? That's real power. That plus the actual power that's absorbed by that load of 88 is the total power supplied by this voltage. Do you follow me?
So it's no longer divided by 2 because we're using RMS.
That's right. And by the way, all our power problems will use RMS voltage and current. You'll notice how it has a sub RMS for the current and it has an sub RMS for the voltage. And I hope you can see that right there. And I'm sorry that the resolution isn't better. Are you with me, class? Now, this is important. I have the magnitude of the current that I used to calculate the power lost here. Now I have this is the total power. And that's what they wanted, the total power supplied by this voltage source. To many, it will seem trivial because what you're saying is I have 3 of the 4 that I need to solve the equation where the power is determined in terms of the voltage and current power factor. I calculate the magnitude of the current, then I calculate the magnitude of the power lost here, and I add the 2 powers together to get total power supplied. Do you follow me? Now here's something very important that I'm going to add, and I want to make sure everybody sees this. If this 480 volts, and he didn't do it for a reason, is actually going to be 480 volts, VRMS, at an angle of 0 degrees. Now listen carefully. And now I want IRMS in terms of a magnitude in the angle. I know IRMS is right here, right? That is IRMS in terms of the magnitude, right? Please listen. How do I get the angle? All right. Anybody?
The power
You have
factor.
Say again?
You use the power factor because
You're right. But what do we do with the power factor? Anyone?
Use the angle because it says it's lagging. So you know.
Yeah, but there's something, the essential is what? Take the inverse cosine of the power factor, correct? Right? The cosine of theta V minus theta I is the power factor. If we take the inverse cosine, then we have theta V minus theta I. Does everybody understand what I'm saying? How many do? Just some indication. Heads nod or hands? Good. All right, so if I take the inverse cosine of 0.707, does everybody see I get 45 degrees? How many see that? You would get 45 degrees, would you not, class? Inverse cosine of 0.707 is 45 degrees. Give me that, guys. All right, now, I know theta V minus theta I would be what, 45 degrees, or the current, when they say lagging, the current's going to be behind the voltage by 45. So the current here would be minus 45 degrees as far as the angle. Do you see it now? Please indicate if you do or not. Thumbs up or thumbs down? All right, good. Now, that's a classic problem that you'll get on the fundamentals in engineering exam if you take it. And I encourage everybody to take it. There is no downside of taking it. If you pass it, it may help your careers, especially in about 3 to 5 years when you can go up for your PE license, okay? I have an FCC second class. I passed the fundamentals. It used to be called the Engineering Training EIT years ago. I never got a state license in Alabama because I never needed it. But if I do, I would, and I still may. Now, getting back to the problems I pasted up for you. By the way, yeah, the class technically is over. I had some technical difficulties yet again, and I apologize. This is officially an office hour. Before I start the office hour, are there any questions you want to ask? And I apologize for going 3 minutes over according to my clock.
I have a question. Is the quiz going to be Friday?
I'm glad you asked that. Reluctantly, no. I mean, I wanted to do it on Friday. We have a game, don't we? Don't we have
Yes.
Arkansas here?
We have a home game.
All right, how about this, if you don't mind? I will forego the quiz on Friday, and I'll give you some information after I consider this. I may poll the whole class on this one, about when to schedule the next quiz. Now, our test is coming up towards the end of October, is it not?
Yeah.
So today is the 7th. Let me take a look at this and get a little more information. I hate not to miss a quiz, but right here we're at a point where we have a golden opportunity to make some real progress and catch up to where we should be. All right, other questions? That's a great question. I'm going to use that time to catch us up so we don't have half a class just for a quiz. Anything else? Questions related, because for those people that can hang on for a second, because we're going to be then doing more of this, and any other questions you have. Anybody?
So something you said earlier about European power,
Voltage and actually.
voltage and frequency. Well, I bought a power supply for my computer over the summer, and it had a different rating for efficiency.
Don't worry about efficiency. That has nothing to do with voltage or current or frequency. What was that? Oh, never mind. All right, class, bear with me now. I'm going to do one thing. I don't know if this is going to work, but I'm going to try to change this resolution. And guys, if you can give me any tips. I had 640 by 480. I don't know if it'll take 1040 try, right? Better?
Better.
Am I getting any lag when I move like that? No?
Well, where are you moving?
I'm moving my cursor. Can you see it? How about here? You see any lag with the hand?
There's definitely some lag.
With the hand?
Oh yeah.
But your resolution here is better?
Definitely.
Yeah, it is.
All right, well, I'm going to try it this way, okay? And I'll write slow. How's that? Just bear with me. Now, the thing I want to get at is this. I would like to do a few more classic problems. Those that can't be with us will pick this up. Now, any other questions before I move on to this? This is really kind of the meat of this chapter right here, and then we get into three-phase. Go ahead, Joseph.
Oh, you never co-hosted me earlier, so I guess I can still record the.
You're going to record as my, I'm sorry about that. Here, make co-host. How's that? Does anybody else want to be co-host? I don't mind making the whole class co-host if possible, so you can all record it, have your own private. Really, I'm trying to be as good as I can with this material. The more sharing, the more discussion you have, the more you'll retain. Really. And I don't get on GroupMe. I don't know what's going on there. But I promise you, you can never get too much interaction about things unless it gets to a point where they're asking about other things. Go through some problems, and you've got these problems and you've got the solutions as well. So I want to go ahead and take a look.
So Dr. Baginski, when I tried to start my own recording, it just paused the cloud recording.
I think
So,
it's already recording. I had the same issue, so I just let it record. It shows recording. I'll see if it's going to save after.
So what I think is happening is it's recording everything we're doing to a cloud. So all three co-hosts can only interact with that cloud recording, and they can't start their own local recording.
I don't know what to tell you. Jessica, do you have any suggestions? You've done this before.
Yeah, I think right now for both of us, it's showing that it's recording, but as he was saying, I think even after it finished, yours will still be fine. We'll still see it on Canvas. For this, you actually have to log in onto your Zoom account and try to find the cloud. Yeah.
All right, Grant, you asked about the class on Friday being on campus. No, if I'm only trying to do what was polled by the class. They did not want an in-person class. I would just assume have classes in person. Be a lot easier for me, for starters. and hopefully it'd be better for you, but the class didn't want it. We did a fair poll on that class. I mean, I'm not gonna start trying to, you know, jimmy things up to get things my way. I just told you that that's the results of that poll. Unless there's an obvious reason to, you know, forego that poll, then I have to honor it, because I said I would. Now, I want to get to a problem, all right? I want to show you this applied to a real type of problem. The problem I'm going to start with is 525. This problem is up there. If you have OneNote, you can open it up on OneNote. But here's what it says. A load operates at 20 kW at a 0.8 power factor lagging. And it says the load voltage is 220 at 0 degrees at 60 hertz. When they say load, it means the load that you're interested in, like that 480 was across. So let me draw this first. So you always start when you do a problem. This is going to be 525. Now, I know there's lag there, but can you see it okay, Brantley? All right. Now, draw this first. You put your load here. That just, you know, identifies the load. And here it says it's 20 kW, so put P load is 20 kW. And it says it's a lagging power factor of 0.8, so you can put power factor is 0.8 lag. Just put that down. And the voltage is 220. It means the voltage from here to here is 220. 220 volts RMS. And it's at 0 degrees, so you can put 0 degrees here. And again, this is 525 if you have OneNote available and you want to pull this problem up. They say it's at 60 hertz. This won't matter now. It will later. You can just jot that down. How come this, there we go. This is 220, and I'll try to write better. And then it says the impedance of the line. Now look, it says right here, impedance of the line. That is not the load. Do you follow me? That is the actual connected, I'd say, power line. So right here they have an impedance, and it says it's 0.9. So the resistance is 0.9 ohms. And the impedance, or the inductive reactance, is J0.3. And they say determine the load voltage, determine the voltage and power factor at the input. This is called the input, and it's really at the power company side. It's what's being generated by the power company. They want both V here, VRMS, and that's at the source, and they want the power factor here. Now, does everybody understand the problem? They have 220 volts at 0 degrees here. This is called the load. You good with that? What do we have, 13 participants now? That's okay though. You know what it tells me? I mean, some people have classes, they have commitments. I wish they were all here. But those that you are here, hopefully you'll benefit from this greatly. By the way, I didn't mention this, but the average grade in the quiz was very high. There were a cajillion seemingly 10s. Did y'all get your quiz grade? Just checking. All right. I don't know how many got 10s here, but there are a whole bunch of them, and I'm glad. I say this again. I am very pleased or glad that there were so many very good performances. It tells me that people are getting it. And it wasn't meant to be tricky, but no matter what I say, it will be tricky for some. Are you all with me? Okay, bear with me on this. So right off the bat, we focus on this, the load, and we want to get the actual peak or the magnitude of the current. So I like to draw it this way, and I'll just call this IRMS. I'm going to start dropping the RMS because everything is an RMS when you do power problems, okay? Now, I know if you want me to, I'll isolate this. I've got a voltage from, this is just the load, a voltage of 220 volts at an angle of 0 degrees. That's RMS voltage. I have a load here that's 20 kW, kilowatts, and I have a power factor of 0.8 lagging. Correct, class? Now, what I need to do is get this current I, and I'm going to stop the sub RMS. It's implied, if you're okay with that. Now, go back to the equation. The power, that's average power, or the load power in this case, is equal to VRMS, that's a scalar magnitude, times IRMS, right? Times the power factor. That's the equation I'm going to use. And what I'm after is IRMS. So I rearrange this. And I say IRMS is equal to the power, that's real power in kW, divided by VRMS, divided by the power factor. Do you all agree with me? Or it's equal to 20 times 10 to the third, divided by VRMS, which is 220. You don't put the angle there. And the power factor is 0.8. So I'm going to go ahead and if you don't mind, get an octave up. I don't know if anybody here uses Octave or MATLAB, but if I'm on a computer, I usually use MathCAD, but I'm not going to bother with the MathCAD right now because I have to phone in. Come on, Octave. If you want to get your calculators, please do. And I'm just solving this. I have no idea why this is so slow. Oh, now I see. All right, now for this one, I'm going to go ahead and put it, I'll just put PL right here is 20 e to the third. V is equal to 220. What else? PF is equal to 0.8. So I'm putting all the values right there in memory. Then what did I do? Oh, right there. Now, the next thing I want to do is get I. And I can call it IRMS if I want. So that's PL divided by V divided by V times PF, right? And I get that for the magnitude. You all can see that, can't you? My screen?
Yeah.
Now, the next thing I need, I've got a power factor of 0.8. I need the angle associated with that power factor. The cosine of theta V minus theta I would be the inverse cosine of 0.8. So I'm just going to say ANG is equal to, and I think that's A cosine of 0.8. Now that's going to be in radians. So I multiply that by 180 and divide by pi, and that'll give it to me in degrees. I get 36.87 degrees. You agree with me, everyone? That tells me the current is going to have a magnitude of 113.84, and the angle is 36.87. Are you with me? I'm going to move this just so you can see this. So I've calculated both current and magnitude. All right, now, when I look at this problem here, I have this current, right? I know this is 220 volts, correct, class, at 0 degrees. I want to wait for everybody. I can see 1, 2, 3, 4, 5 people. But there are more than that here. I'm hoping you all are with me. Are you guys? All right, now what I need is this voltage. Now follow me on this. If I start at the negative terminal here, I would get an increase at 220 at 0 degrees. This will be RMS voltage. Do you agree with me? But I still need this voltage, right? Now look, the current's going this way, right? So wouldn't the voltage from here to here be equal to I times 0.9 plus J 0.3? Wouldn't this be the voltage, and I'll call it V line right here, plus to minus? Do you agree with that, everybody? If I know the current, I, and I do, then the voltage across this element would be the current times the impedance. The impedance would be 0.9 plus J 0.3. Do you agree with me, everyone?
Yeah.
I'm waiting for everybody to make sure. Okay, thank you, Jenny. All right.
I have a question about this power factor thing for the I. Why is the angle not negative if the V leaves the I?
It should be, and that. Thank you so much.
Oh, okay. Thanks.
I'm so sorry that I didn't put that there. I know it's lagging. I hopefully would have caught myself. It should be negative. I'm glad you caught that. Yes, it should be negative. I made the classic mistake, not intentionally either. It's negative because the voltage is 0 degrees. So if it's lagging, the current would be behind it by that angle. Thank you so much. Are you good with that? I hope a bunch of you saw that and didn't say anything out of politeness. Please be impolite. Let me know. The more I know is wrong, the better I feel about the class as a whole. If you catch my mistakes, I'm very happy. Now, if that's it for the actual current, now listen, now would you agree that this voltage, and I hope you can see this from here to here, that I put with that purple kind of thing, that voltage would be equal to the current, right? This is the plus one, times the impedance. Do you agree with that? All right, so I'm going to go back to octave if you don't mind to get it. All right, you all have that. So I'm going to go here, and now I'm just going to call that VL. I'm going to say VL is equal to here. It's going to be I RMS, right? We calculated that right there. And I got to put the actual angle in here. So I'm going to do EXP right there. Because it's minus 1J times, and it's really the A cosine of 0.8 because it would be in radians. Oops, sorry, this is I. I'll just call this I right here because it's actually the magnitude times that. So that should be the actual I with real and imaginary components. Because I is going to be lagging. It's got a magnitude and an angle, right? Does everybody understand what I've done there? I have to incorporate the angle, and the way I do is I use an exponential, exp to the minus j, right? And then the angle would be here in radians, not degrees. You got that, everyone? You could take the cosine of the power factor minus j times the sine of the power factor, multiply it by IRMS and get the same thing. I just chose to multiply it by e to the j, that angle, and it'll do the same thing for me. Now, if that's I want you to listen. If I want the voltage on the line, V right here, V line, now I take that current I. Again, it's complex, right? It's got a magnitude and angle that I've already taken care of, times the actual impedance of the line. And the impedance of the line was what? 0.9, right? plus 1J times 0.3. I hope that's right. And that should be the voltage on the line. That's V line times. Sorry, right here. Does everybody agree with that? Now that's just the voltage over that, you know, bit of line connecting. Now, what is the total voltage? V or V of the source, Vs. That would be 220. I'll put down 220 at 0 degrees, right? Plus the actual voltage on the line. And that would be the voltage at the source or at the power company. Does everybody agree with me there? If I'm going too fast, yell at me. You good with that? Thank you. Thank you. All right. Now, I'm still not done though, right? What I need is both the magnitude and angle of the voltage at the source. I'm going to go ahead and do this in its entirety. So the magnitude's pretty easy. That's ABS of VS. That's the magnitude of the voltage at the source, which is 324.07. And then I need what? I need the angle. So that would be what? The angle, I hope this is it, angle of VS, right? Angle of VS times 180. I'm going to put it in degrees, divide by pi. So that's minus 6.0385 degrees. Do you agree with that? If anybody else is working with me. Now remember, that's in degrees, correct? But if I want the power factor, now just hold on for a second. I'm sorry, this is the voltage. This is the angle at the source voltage. And we already have the current, and the angle at the current is 36.870, but it's negative. So let me redraw this and talk just a bit about it. I'll get you all up here in 1 second. And I hope everybody has access to this.
You got your calculator blocking your dot cam.
I know. Don't worry. I'm going to get it out of the way in 1 second. I'm just redrawing the circuit here. We had the current as, you have to forgive me, I got to pull this up. We had the current, 113.64. And the angle is minus 36.87 degrees. The angle here was 0 degrees. We found this voltage V source to have a magnitude of 324.07 volts, right? And the angle was minus 6.0385. I'm just going to leave it minus 0.063 degrees. Doesn't It doesn't really matter at this point. Do y'all follow me? Now, hear me now. Now we want the power factor, the power supplied by the source and the power factor from the source, right? So really, we want to know what the power factor is for everything on this side. So what we do is we have the voltage and we have a current, right? We have this current, still the same current, and we have this voltage. Now the power factor is what? It's theta V, which is minus 6.03 minus theta I, right? Can you all see that?
Yes.
Now what is that? Minus 6.03 minus a minus is plus 36.87. It's about what? Minus 30 degrees. Do you agree with me? Or I'm sorry, it's about 30 degrees. Agreed, class?
Yeah.
Now, can you see it's still lagging, right? This current, this angle is less than this voltage, so it's still lagging, right? The current is lagging behind the voltage at the source. Can everybody see this? So if we take a look at the power factor at the source, it would be the cosine of theta V, 0385 degrees, minus a minus or plus 36.87 degrees. Now, whatever that cosine is, it is. And guess what? It's going to be greater than 0.8. I don't know how much greater, but a little greater. I can do it for you. Somebody else can do that. About 30 degrees. It's pi over 6, right? So it's about 0.866 if you do it. Anybody can do it with me. But it's still lagging, right? How many see that, what I'm doing here? The question really was, they want the voltage, determine the voltage at the line. That's this voltage, it's at the sending end, and the power factor at the line. And if you look it up on OneNote, and I don't have OneNote open, you're going to find out that this is going to be very close to the voltage, and that will be the angle. And the power factor is going to be about 0.866, about, and it will still be lagging, LAG. Okay? Do you follow me? How many do? The key is getting the current through the load and the angle of the current through the load. Want to try one more? I mean, I would like to, but if you've got other things to ask me, please do. Now you have these, I put them, and I've done this for a reason. These problems, in my opinion, are not that difficult, but they do one thing better than most books that I've ever found. They really focus in on the concept, not a lot of extraneous stuff. And they do a real good job. I don't know if you can appreciate this with the problems I've given you, but they hone in on what I'm trying to teach. So if we look at the next one, before we write it out, just take a look at this. You're going to get some of these. They says a particular load has a power factor of 0.8 lagging. We know it's a, huh? Sorry. This is 26. A particular load has a power factor of 0.8 lagging. The power delivered to the load is 40 kW. It's 220 volts. If they don't specify it, assume it's at 0 degrees. If the transmission line has a resistance of 0.8085, determine the real power that must be generated. Now this one is pretty straightforward. And I want to just listen to me. If you look at this information, they have a voltage, they have a power factor, and they have a power. What they don't have is a current. Do you all see that?
Yeah.
So if we take the power, 40 kW, divide it by the voltage, 220, and divide it by the power factor, 0.8, we get the magnitude of the current, don't we?
Yes.
Does everybody see that? Jenny, are you okay with that? And Jessica and Andrew?
Yes.
And Brandon, thank you. All right, now, if you have that information, are you in the library, Brandon? Are there many people there?
There's a few, but not a ton.
How about on campus? Are there a lot of people or not?
Not really.
I was on campus yesterday and I was kind of shocked by how many people there were. Like, I thought it'd be a lot more of a ghost town, but it's like average during, like, between classes, like what it used to be during class time. Like, people are just out wandering around without masks on.
Is parking bad or no?
I didn't have to park.
I have things I can do on campus. I wouldn't mind going up there, but
I mean, I parked at the library, and it was like half empty, or it was at 9 this morning.
that's great. For me, it's great. All right. Y'all agree from this one we can get the current pretty straightforward because we have 220, right? I'm sorry, we have 40 kW and we're going to divide that by 220 and 0.8, right? So we can get the magnitude of the current, right? Agreed?
So the 220 says 60 hertz line. So is that?
Doesn't matter. That's just additional information.
Okay.
Doesn't mean it doesn't you don't use it. The only thing you do on this one, you're going to calculate the magnitude of the current. And once you have the magnitude of the current, you take that and square it and multiply it by 0.085. And now you have the power that's actually dissipated by the line. Do you follow me?
Yeah.
Add that to the power that's already being used by the load, 40 kW, and that's the power supplied by the source. That's how easy. That was like the example problem we started with. Jeannie and Jessica and Andrew, you good with that too?
Yes.
Good.
Does
Yep.
the 60 hertz ever come into play?
Not yet. It will.
Okay.
It comes in with when we do something called power factor correction. And that's coming up, but not right now. I want you to get acquainted with power factor and how to use it. Now, what about we could do this one, but this one is sort of, it's very easy, if that makes sense. Go to the next one and we'll draw it out if need be. Here, I've got a line voltage of 220, got a load of 50 kW. Those are all familiar, right? Then I've got a power factor of 0.75 lagging. I've got a line resistance of 0.1. Determine the savings in the line losses if the power factor is somehow changed to 0.92. Let me tell you the issue here. And this is where you're going to appreciate. How many of you guys are industrial engineers? How many people out there are industrial? One? Only one of the bunch left. Joseph, what are you? Mechanical or electrical?
I'm materials.
Materials? Brantley materials or aero or what?
Arrow.
Aero. Jeannie?
I'm Aero.
I couldn't hear you.
I'm aerospace.
Aerospace. Jessica?
I'm industrial.
One and Andrew? Sorry. Industrial engineers need to be really acquainted with power factor because the closer you can get the power factor to the one, the cheaper it is for your plant to operate. Y'all with me? So this is a typical industrial engineering problem. As a matter of fact, you'll probably see something like this on the FE exam. That's the reason I'm going to spend a little more time on this one. So I'm going to draw this problem. I know I got this thing here. Let me see if I can move it. next time I think I'm going to have MathCAD up and you're going to see how quick we can do these problems. Literally, I can buzz through probably 8 or 9 of these in under 10 minutes for sure. 5 minutes typically. All right, for this one, it says, it starts out like this, and this is problem 527. It says they got an industrial load of 220, and it's 50 kW. (220 volts) at 0 degrees RMS. The power being used is 50 kW. And it says it's got a power factor here of 0.75 lagging. By the way, almost every power factor you're ever going to run into in industry will be lagging. I'll repeat that. In the real world, almost every, I've never seen an exception to this, will be lagging. The reason for that is any kind of rotating machinery, any industrial equipment that has coils of wire will have a lagging power factor, and that dominates production for an industry. All manner of industries, including robotics, things like that. So that's lagging. And then they have a line resistance of 0.1 ohms. So draw this here. That's called the line. It's simply an electrical line that connects to it, just like an extension cord. And then they have a source voltage. This you could talk about as the power company. As a matter of fact, when you get into power in your course in industrial engineering or how you deal with the actual power company, they'll talk about power companies and the way they charge for different power factors per hour. So when you have this, they want to know what the total power supplied by the source would be. So they want to know P supply. That's what they're up to. Are you with me?
Yes.
Okay. And if you follow me on this, how am I going to get P supplied? Well, right off the bat, I'm going to get I, right? So I'm going to start by saying I would be equal to what? 50 kW, right? Divided by 220, divided by the power factor of 0.75. That would be I's magnitude. Do you agree with that, everyone?
Yeah.
I'm not going to do the calculation yet. With me, everyone?
Yes.
Now, with that, the next thing I'm going to do is find the power supplied. And here, P supplied would be equal to the power already being used, 50 kW, right? Plus, then I'd have to take the power being used by that. And that would be what? That power would be 0.1 times I squared. So whatever that is, it would be the magnitude of that squared. Do you agree with that?
Yeah.
Thanks, Chief. Jessica, you can leave your mic off. There's not enough. If you guys just want to leave your mic off, it's fine. I don't think, unless you got Led Zeppelin in the background or something, I don't think there's going to be a problem. We've got what, 5 people on here besides myself? So now I'm going to go ahead and just do it. I'm going to bring this over here. And if I look here, I should show you how easy it is with MathCAD. And I should do it to everybody. I'll do it here. So the first thing is, I'm just going to go ahead and I'll just put down I. Here, not that one. I here is going to be equal to 50,000 or 50 e to the third divided by 220. times the power factor is 0.75, right? So that's the I, and the next thing I get is the power supply. I'll just call it PS, and that's equal to 50 kW. Right, 50 e to the third plus, and it's going to be, the resistance is 0.1 times I squared. And so that should be the power supplied. Do you agree with that?
Yeah.
All right, now problem changes. How much power is supplied? This is part 2. When now same amount of power being used, but the power factor goes down from 0.75 to 0.92. So now the power, or the actual,
Octave is covering the screen for the cam.
thank you. So now I'm going to go ahead and say the power supplied would be equal to, I start here and I first got to get I. Here I still 50 kW being used, still 220, but now the power factor is 0.92. That tells me the current's less, right? I'll get that. And once I have that current, then I get P supplied. And that would be 50 times 10 to the third plus 0.1 I squared. And now I'm going to bring over octave. And I come over here, and from, instead of 0.75, I put 0.92, right? So now my current goes down from 303 to 247, and that's the real thing. When you reduce, when you get the power factor closer to 1, the amount of current goes down. And that means the losses in the line go down. And the next thing you do is get total power supplied, which is 0.1 I squared plus 50,000. And you see it goes down to 56,102. It was 59,182, right? So the savings would be 59,182 minus 56,102. That would be the amount of power that you actually saved at the source, and that's how much it cost. The power, sorry, whatever industry was using this would literally save that much money per kilowatt hour. I mean, it would be less that much power. Now, I don't know what a kilowatt hour is these days. I wish I did, but I don't. But some of you will have to know this kind of information, namely those that work in an industry. If you're any kind of manufacturing, and I don't know anymore where people start, but if you do any kind of you're involved with manufacturing, Detroit for motor cars, if you're out on the West Coast, you're making computers or making parts for Intel or something like that, anything where you've got a foundry or an assembly line, anything like that, power factor is critical. And we're going to get into this, and it's a little advanced now, but the way you reduce the power, or I'm sorry, the way you increase the power factor to get close to 1 is they add large banks of capacitors in parallel with the actual plant voltage, and then you can get it almost at 1. And that's when you get the minimal cost to the actual business that's using it. Now, one other thing, somebody's going to say, well, what about our homes? This is a question I get. I'm going to address it right now. And I know it's out of focus. Well, it's in focus now. What we have really when we deliver power are what are called three-phase power. Now, I can't get into all this right now, but there are 3 voltage sources, each of equal magnitude, separated by 120 degrees of phase. That actually is the way power is delivered. There's a reason for it, because the average power and the peak power are the same over the transmission lines. In industries, they use all 3 phases of power when they do anything, and I can't get into that either. with the home utility, you really have this right here. You only have one phase and you have no power factor correction on your line. So the line, and I'm just going to tell you people this since you're hanging on, and you probably are interested in this. This is in the state of Alabama and just about all the lower 48 as far as I know. On the pole that you see up there that delivers power to your homes is a transformer. And it, on our side of the transformer, it has plus and minus 120, and it has a neutral line. So you can get as much as 240 volts, and your dryer will run on 240 volts typically. Some other things in your house, your water heater, if you have one of those, hot water, and your heat pump. But on the other side of that, there's a transformer. On the other side is about 7,200 to 7,700 volts. That's a high voltage. That has something that will, there is nothing that stops the current in that one until it's extreme. So if you're on the other side of that, if for whatever reason you do something really dumb and throw a copper line over the other side of that one and you're holding onto the ground, you can kill yourself. And there's nothing that could stop you. When lightning hits and you see the flash in your house, it's because lightning hit that side of the utility, the 7,200 volt line, and literally arced to ground, making it a short, and it basically shorted out that thing for an instant. It'll flash. You'll see like a flash in your house when that happens. Lightning can also hit the power transformers and blow them up, and there's other things. But typically that's where lightning hits. The 7,200 volt side is the dangerous side. Don't ever go up a utility pole and get on that side unless you know what you're doing. You can kill yourself. On our side, it's very hard to kill yourself with 110 volts. I can grab 110 volts. It might give me a little zap, or 117 volts. 117 is really what it is. It might tickle me maybe if I have moist hands, but you can actually hold that with dry hands. 220 you can hold too. It's a little more. Now, 7,200 volts, if there's nothing that limits current, will kill me. If current is limited, you can actually not be killed by it. But that's something else. And I'm telling everybody this because, believe it or not, engineers have a way of killing themselves faster than any other group of people except rednecks in the backwoods, because rednecks try to string up stuff. And I've literally seen stuff where, I say rednecks, I'm a redneck. I mean, I went deer hunting and stuff, and I always thought I was smarter than everybody else. And I've done really stupid stuff. But I'm telling you this for your own good. I have seen this with my eyes. I didn't believe it. People will go out there and they will see a utility pole and they will try to go ahead and just hook a line up there. And if there isn't a transformer, they will try to tap into that 7,200 volts, bring it down into their, I don't know, their deer camp or whatever to heat something up. And then they will usually either burn down the cabin or something like that, or may kill themselves. They do all sorts of, some of them work on the other side where there is a transformer, but they don't know about some standard safety measures like a grounding rod and other things that I'll cover. And they almost kill themselves. I have literally been in, I'm only telling you this story because some of this stuff may save your life at some point. If your boyfriend or somebody you know is doing this, you might save their life. I have been out there at a place remote when I was fishing, and I heard this buzzing. I'm like, what is that buzzing? Somebody had hooked up a line. No, I don't think they had a clue what's going on. Without a grounding rod from a, it was a plus or minus 120. So at least they were on the side of the transformer that usually doesn't kill you, down to a hut. And they had literally currents being shunted through, I'm not even sure what it would be called. But it was buzzing because there was a, you know, if you have, I don't know if you've ever heard this, if you have any kind of metal coils that are light and you run current through them, they attract and they'll vibrate at the actual frequency. Well, they had some coils of wire that were being used, and I'm not even sure what they were using them for, but they had coiled them down next to each other and they were literally humming at that frequency. Now, at some point, they're going to short together. And if there's no fusing, then there's going to be one heck of a fire in that place. But I've seen this with my own eyes. I've seen all sorts of stuff. And by the way, down in the state of Alabama, you do not need an electrician's license to do modifications in your house. This is a word of caution to you. So you can kill yourself very easily in the state of Alabama. And be careful. I'm warning you now, be careful, especially when you're rigging stuff up out in the woods. And don't let anybody say to you, I saw this on YouTube, because that doesn't mean anything, except that guy on YouTube may want to try to kill a whole lot of you. All right, now I'm done with that, but I always try to say that at some point. I'll say it again in a shorter amount of time. Do y'all follow me what I'm doing here? In a nutshell, that's the problems you've got, because, and I think you can follow them. You want to try one more and just tell me how you do it? How about we all take a look at 28 without me going through and doing it yet. All right, can you all see this? By the way, you have these on your, on OneNote. And so you all have the problems and the solutions, right?
Yeah.
Yes.
Thank you for hanging on. All right, for this one, they show you the source, they show you the line. This is the electrical line. By the way, this is a very large amount of resistance and inductive reactance for a line. This would be like the amount from Martin Dam to Auburn, Alabama. I mean, when you get 30 ohms on a line that's supposedly delivering power, that's an enormous waste. You follow me? Normally, it's much less, probably, but 30 plus J5, but this is just a problem. So they say they've got, they're saying, what is VS? They don't know what VS is. That must be supplied, so we have 2 kW. So right here, they give you the power, and they give you a line voltage. See that VL right here? That's 240 at 0 degrees. Can you all see that? You can't see it well. If you look on your OneNote, you'll see it. This is VL across the load. It's 240 at 0 degrees. All right, they want to know what this is, but they say here you got 2 kW. They got 240 at 0 degrees. And they got a power factor of 0.8, but look what they say, leading. Leading. Which means whatever the voltage is, the current's going to have a positive, not negative angle, right? Okay. Yeah. So taking a look at this one, right off the bat, we can calculate the current, right? We can say if we take 2,000 divided by 240 and divide that by 0.8. So 2,000 divided by quantity 240 times 0.8, we get the magnitude of the current. Do you all agree with that?
Yes.
I know I'm just talking. Brantley, can you hear me okay? I mean, you got me, right? Are you with me? And Andrew, if you're there, you got me? Okay, I'm assuming it's okay. Anyway, I need the angle though. You'll notice the power factor is leading. So I take the inverse cosine of 0.8, right? And I get it in degrees. I think that's 36 degrees, but you can check on 36.8, I think, but you can check me. I'm not actually sure on this one. Might be 26 point something. But take the inverse cosine of 0.8 in degrees.
36.87.
Okay, I was right the first time. I've got that. So now I've got the current. And if anybody wants to do this calculation, go ahead, because I can bring octave into it, but I prefer not. But you can go ahead and get that, right? Now, once you have that current, I've already got this voltage. To get this voltage, I just say I come around here, I get an increase of VL at 240 at 0 degrees. Then I get an increase of 30 plus J5 times that current, right? Good with that, everyone? If you didn't hear me, what I'm just trying to, maybe I should do this. Y'all, I'm going to try right here to, no matter what I do, I don't think I'm going to do justice to this. Is there a way to collapse this? There is, isn't there? Oh, better yet, let me go on this side. Nah, I ain't going to do it either. Give me one sec. I don't know if this is going to work. Ah, it did. Thank God. All right. Follow me on here. I'm just going to go ahead and first find the current. And we had 2 kW. So this is 2000, right? And then we had 240. So this is 240. And we had a power factor of 0.8, but it's leading, right? So that's the current. You all agree with that?
Yes.
Now, the angle on that is going to be the inverse cosine of 0.8, which you said is 36 degrees, right?
36.87.
So that means the current's leading by that much. Now, I'm going to go ahead and say I call it I1. I'll call this I1. Better yet, yeah. Call it I1 is equal to I times EXP, and this is going to be 1J times a cosine of 0.8. So that will be in radians, and that means this is actually the current, real and imaginary part, and it is leading. Now, when I wanted to get the total voltage at the source, that's going to be the source voltage, which is 240, plus, and then I have to take that current I1 times, and then the load here is 30, right?
Isn't the... Oh, yeah, it's fine. I was curious about why it wasn't squared, but I realized you're calculating current, not power.
Yeah.
Ignore what I said.
I'm not going to calculate power yet, but we can. So it's going to be, the power would only be dissipated in the 30, by the way, 30 ohm. It's going to be 30 plus J5, right? And that should be the voltage at the source. I hate when this happens. It should be 5J. I think this will do it, I hope. Yeah. So that's the voltage at the source. Right? Because it is leading. And then if I want the magnitude, I take ABS V source. And if I want then I can get AG source. Angle of the source is going to be 26.544 the source. So the power. So that's the voltage. And we could calculate the additional power too by just taking 2 kW plus I squared times 30, right? If we wanted to find out how much power is supplied by the source. You okay?
Yeah.
Everybody okay with that? All right, I think the rest are more or less cookie cutter problems like that. But I mean, they're the same basic thing. If you look at them. Can anybody, any of you guys access OneNote and make sure that all these are accessible before I say anything more? I just want to make sure you've got them. While you guys are doing that, I'm actually going to try something here.
Yes, the solutions and problems are in OneNote.
Excellent. Hang on with me, guys. I'm going to try something. I know it's going to get slower, but I'm doing this to see something. Come on. All right. I think you know where I'm going with this. I'm trying to make sure I get as much as possible in terms of the real estate here with clarity so I can discuss things without doing a whole lot of zooming in and out. Can you all see that? Pretty good, Jessica? Can you make, I mean, can you see these problems? And I probably can get some more light in here, but you good with that? I mean, you've got these.
I can see it.
Yeah, I can see it. Yeah.
Now, all the problems, if you look at the next one, it's the same basic thing, right? They give you information about a load, they want information about the source or total power supply, or vice versa. And it'll be either they'll give you the voltage at the source, they'll want to know how much voltage is delivered to the load and how much power is delivered, or any of that combination of that. But that's the essence of this, all right? And this is considered one phase of a three-phase system. Now, any questions you want me to address related to this or anything else? Because we could just do problems after problems, but really it helps you. By the way, I don't know how you guys did on your quiz, but if you've been doing the problems, that quiz should have been pretty clear to you. It should not have been in any way, shape, or form tricky. If you have been doing and keeping up with this, the problem was really just what? Current division, right? And after you had current division, you just found the power associated with the resistance by taking I squared times R divided by 2, because that was I there was peak, right? And that was it in a nutshell. And I don't know what the average was, but it's probably very high, because when I saw the number of 10s, I was very happy, 10 out of 10. I figured you guys are getting it. And I didn't get any hate mail on that one, which I was happy about.
The average was 7.5.
He's averaging the zeros then, because if anybody that doesn't take it gets a 0, so it's probably, the people that took it's probably a lot higher. And I'm not going to say anything about, he's doing a great job, but you know, the problem is he's got a grade sheet, and if you don't take it, it's a default 0 until the grade is replaced. But we have all the ones that are, all the ones that have university approved excuses will be replaced. So I got a feeling, so if we neglect them, it's a lot harder. Because only what? There were 70 people on one quiz. I think there were, I don't even know if we tipped the scales at 80 last time out of 95. So that means a bunch of those people still have zeros unless they drop the class. I was good. It was good to see them. Other questions, guys? You getting it so far? All right, remember, average power, average power is key here, and so is RMS values of voltage and current. And most, if not exclusively, what you're going to get in the real world, mechanical, aero, industrial, civil, chemical, when you work almost exclusively, the voltages you'll be given, like 117, that's the actual RMS voltage. It's not the peak value. That's the way it's done. We start with peak because when we're in electrical engineering and we talk about the waveforms, we always want to use the peak value on the cosine waveforms to describe them for a variety of other reasons that have to do with component values. Like if you have a peak value of 300 volts, your component has to be able to take at least twice that voltage, typically when you design it. That's just a standard design requirement. All right, nothing else? Nothing?
And like, can we just go like step by step, not like to do an exercise, like once you have the problem, the first thing you calculate, would it be the I? And then
You don't know because it depends what's given.
depends what's given,
Yeah, you remember the key thing is know the equation. Average power is equal to VRMS, IRMS power factor. Power factor is cosine theta V minus theta I, right? And then from there, you can get, if for any circuit, you can figure out, and you have to figure out what's given, what isn't, and work from there.
Okay.
And I'll tell you one other thing. When I see people hanging on this long, it tells me you're serious, which is a very good thing. People that don't hang around and ask questions and don't, those are people that I'm very concerned about, because, I mean, if they can't, they can't, but you know, I'm a faculty member. I've got a lot of things to do, but I'll make time for students here because it's such a large class. And also, I know there are some people in this class that probably have not had the amount of training, and it's important in this area. It's important that you do well in this for all engineering. I don't know how you get away from electrical stuff these days if you're a mechanical or an aero guy. Industrial, yeah, I can see you can get away from it, but mechanical, aerospace, I mean, with the amount of different things where they have UAVs and all the stuffs for controllers and stuff, they're all controlled by electrical systems. And frankly, it's digital systems, which is another thing I'd love to teach if I had the time in here. Because that's, you know, when you buy chips and all that, do you guys get anything with where you get a microcontroller and have to program it or not?
I did that for a lab a while ago, where we measure or we got a little Arduino and we had to measure
You
the
got an
engine
Arduino?
force.
Okay, good. You know, you don't know how valuable that is. Everything here nowadays uses microcontrollers or larger scale. They actually use like microprocessors. There's no longer analog systems. I mean, even with modulation, demodulation of AM and FM signals, radar, it's all done by digital signal processing. And that means chips, programming chips.
Yeah, you can't really be an engineer without computer programming right now.
Yeah, not just computer programming, but you have to know how to program microprocessors, which means assembly language, or at least, you know, you program in C or whatever, or, you know, Python or something like this, but it has to be turned into an assembly language code that can be, or a C code at least, that can be implemented. Did your Arduino program in C?
We use like Arduino is like Pinturio, or it was something that came with the Arduino process. It was like MATLAB but simpler, so it might have been based off C.
It was probably R maybe, or one of these languages that's a subset of like C or MATLAB.
It was less intuitive than MATLAB. You had to tell it to do everything.
Okay. Are you sure that wasn't assembly?
It might have been. I don't know. Like I only had one lecture. So do you know Dr. McDonald in biosystems? Well, he is as old farmer redneck as it gets. And we had like a 3.5 hour lab once, maybe twice, once a week, and 2 lectures. And the lectures were at 8 in the morning. And he taught nothing during the lectures. All he did was these wrong rambling stories about how he's at these, like, oh, I was at a drag race out in some, boondock part of Alabama, and a truck lost its brakes and came down a hill and crashed into this, and that's how, it was just this. And then he would give these really good in-depth lectures that would go for 3 hours, 3.5 hours during the lab time, and then assign these massive projects at the end of that would take 10, 15 hours, like a whole week to do. And then like I only got that 1 3-hour lecture on whatever this programming language was.
Are you guys understanding the way I'm teaching?
Yeah.
Yeah, I understood. So, Dr. Baginski, are we still going to see the inductance problem? Because I was thinking that on last quiz, that was going to be there, the inductance problems that we did. But yeah, are we still going to have them on like the midterm?
Yeah.
Because I remember we did one quiz with a capacity.
Well, wait a second. We got over a week for the midterm yet, right? It's over a week.
3rd. Yeah, so
Huh?
it's on the 23rd of this month.
Yeah, but today's what? Today's the 7th.
Yeah. So.
I mean, you still got some distance. Yeah, we're going to get. I mean, you got to be responsible for knowing how to do a transient on an inductor or a capacitor.
Yeah.
All right. I mean, an RC RL problem. You got to know how to solve circuits problems, right? Just look at the past quizzes. That tells you. That's a forecast of what's on the test. And if you really look back at those past quizzes, they're not very hard. In retrospect, they're hard when you first see them. If you haven't established the concepts in your mind, I promise you in this course, if you don't have it down, you will look like LSU did on their first game. You will be wishing you didn't come. I promise you, if you got it, you're going to kill it. I look at the grades in this class. I got 10, 10, 10, 10. And then some people, I mean, they're all over the place. They get like 9s and 10s, then a 0, then 2s. And I don't know what to tell them. It just looks like some week they decide to throw in on it, and then other weeks they're just not there. And I've seen that I've seen that before when I've taught this course. But now I'm seeing as a trend, more and more people are getting consistently more. They're better. They're getting better on every quiz, and you can see it. You can see the performances steadily improving, and that's the great thing. That's what you want to see, because that tells me first exam they're going to be pretty serious about, and then by the final they'll be very serious. And you realize all this stuff builds. You can't solve power without knowing circuits, without knowing, the basic concepts, the voltage current relationship and stuff like this. It all builds. Are you on any of you two on campus or not?
Nope.
Well, I wish I could give this lecture in person. I wish I had a board, because this first time, I guess was I've been lecturing without a board, and I do not like it at all. I can deal with it, but I don't like it. Did those PowerPoints help you guys at all that I gave you before?
The ones with the power?
Let me actually,
Some of the concepts, at first it was a little bit confusing, but then once you explained, going back to it.
Yeah, going through it with you was helpful. Stuff you didn't go through, I haven't even looked at it.
Let me actually see because I purposely got those. And again, I'm not a PowerPoint person, but those things seem to really hone in on this, the ingredients I wanted to. Let me see if I can find them right now and just talk to you guys for 1 second and leave you go. Are you guys having any problems getting to your other classes or anything like that? Anything, because I interact with the provost about stuff. If there's anything you can tell me about that you find is a unique problem that could be solved, let me know. With anything, food, I don't know, drinks.
The only thing I had, the reason I voted against the in-person class was because I have a class right before this.
Mm-hmm.
And so I was for every time we have an in-person class, I'm always 3 to 5 minutes late. So I've got all my stuff set up at my apartment to take that online class.
Oh, it's online.
So then I have to get on my bike and ride to your class, and because your class is usually online, it makes sense to be in the comfort of my own home for the other online class rather than try to set up something on campus.
Well, this is Zoom. When we're there, it's still Zoom. You don't have to be there if you want, unless it's a quiz. If we voted for all in person, then there's still by Zoom. It's just I can't interact with you this way.
Okay.
I suppose theoretically, but it's hard enough interacting with just the class in front of me. I suppose maybe my grader could point out questions from you guys, but that's actually an interesting thought. Maybe if I argued that, if you want to stay home and Zoom, then Zoom, it'll be available. But if you want to be in person, you can be in person. That might be a selling point. That way it's not really an in-person class. It's a blended, and what a blended is.
And then have your TA with a grader with ear headphones on so they could hear questions from the online. He can relay them to you.
And that guy's really good. I want to tell you something. He is super, this guy, Chun Li.
Yeah.
I don't know if you've interacted with him, but he is really good.
I've asked him a couple of questions and he is really on the ball.
He knows his stuff. He's sharp. What?
Yeah. Does he have office hours?
He'll make office hours anytime you need him. I do office hours right after class because that's when I've got everybody here. If I put office hours, I promise you, if I pick an office hour, doesn't matter.
I like this one's right after class. I was talking more towards the quiz because since he's the one grading, so we can go over the quiz and okay.
Oh yeah. If you want to ask questions about the quiz, I'll be happy to talk about it too. But if you want a quiz officer, that's interesting. I'll ask him.
Okay.
He's very available. If you need to talk to him, Jessica, just send him an email. He'll make something happen. Hold on here. I know I have these. Looking for the PowerPoints. Not there, I don't think. Wait, I know where to get them on OneNote. Y'all don't mind OneNote then?
No, it's good. I had like last homework, the one before our previous quiz, I was having problem with the power folder. It wasn't opening. But then once you send it again, I think, yeah, I was able to work with it. But before, during the weekend, Saturday or Friday, I was only able to see the ones with the impedance. I was having trouble with the power. And I think a lot of people had the same issue too. They were saying,
Is that right?
yeah. I don't know if Joseph had the same issue, like the one of the homework with the power one, it wasn't opening. So I was only able to actually work on those power homeworks. I think it was on Monday that you put it again, the day of the quiz. Yeah.
I'm actually not sure, but I know that I got a message. I know on Sunday people were asking me questions, so I assume they saw both, but somebody asked me that they couldn't see something, the problems on PowerPoint, or I mean on OneNote.
Yeah, it was the power one. Mm-hmm.
Yeah, I gave it a shot and didn't load, and then I had other things to do, so I didn't keep trying.
Yeah, you gave it a shot and didn't load. I kept on trying, but then on Monday, I think on Monday it was okay. That's why I had a little bit of problem in this past quiz, because I work a lot in the impedance one, but the power, because it wasn't able to open. I was only able to open the Monday.
Okay, let me see what they got here. Can you all see the screen I'm looking at?
Yeah.
Yeah.
I'm just seeing what he's got here. All right, this is basically circuit analysis. All right, here's the RMS value. Now, I don't even make you do these problems anymore. I mean, you can do them, but if you look at this, it's a simple math problem, right? Take a function, square it, integrate it, and then divide by the period. This is the kind of problem, take the square root of for RMS values. I don't even bother with that because it's straightforward. This is the one I did in class, the square. Oh, I'm sorry. This is different because it doesn't go to 0. It's plus or minus 4. So the squared value of that is 16. And don't worry about that one. Power factor. Yes. Here we go. Power factor. Here he's using peak values. Then he goes to RMS. Can you see that?
Yeah.
This is what I was talking about. Don't worry about apparent. I'll get to that. This is the power factors cosine theta v minus theta. Yeah. Current leads. But you see here, unless I go through a concrete example and give you Eli the Iceman, this stuff doesn't make a lot of sense.
Yeah.
It doesn't. And finally, this is a good one. This is, I think, basically what I did in class, isn't it?
Yeah, it's very similar to
I got 88 kW and power factor lagging, so and 480.
Yeah.
Easily can get the current right here. Yeah, sure. This one, so from 22.
Yeah.
Yeah.
Power savings. There you are, Jessica. You're in industrial. That's what you live for. Saving money. All right.
I looked up the price of power in Alabama right now for residential. It's like 10 cents per kilowatt hour for the first 750 kilowatt hours, then 85 or 0.85 cents. Not 0.85, 8.5 cents.
Let me say one thing. Power is dirt cheap in this state. Power is dirt cheap here. It really is. Go into, now, Jessica, you're from Portugal, right?
Mm-hmm. Yes.
If you're on the Mediterranean, I assume power is fairly cheap. Do you have a lot of wind power or not?
A little bit, not that much.
Is it mainly all coal burning or hydro?
I think it's hydro, if I'm not.
It doesn't matter. If you take a look, I'm going to bet that you're fine too. However, go look at the cost of power per kilowatt hour in US dollars in places like Romania, Serbia, and you're going to see probably a fairly like doubling at least. And Joseph, if you're looking, you can check this out. Now, there's a reason. Well, it depends too. If it's a socialized government, it's a little different. The more socialistic it is, the more the true cost isn't shown in the actual, because they have the government subsidizes a lot of things. But if you get something where it's not heavily subsidized, you're going to see that in those areas, because it costs a lot for them to get external resources. Here in the United States, we have a wealth, and I mean a wealth of fossil fuels, coal and oil and natural gas, tons of hydropower, and plenty of nuclear power too. And it's all here, all right, with exception of we get some of our nuclear materials from Africa, but we got a wealth of, it's not hard for us to make power. In China, it's not hard. Japan is hard. I mean, they do have some, if you really want cheap power, you try it. What France does, they have plutonium breeders, but you got to be careful you don't have an accident because plutonium is very deadly. And, you know, the Russians had Chernobyl, if you look into the history of this. Anytime you deal with plutonium breeders, you got to make absolutely sure there can't be a failure, or else you can get unbelievable disasters. And but plutonium breeder reactors make power dirt cheap, and 90% of all France's electric power comes from that. They were very smart doing it.
The question, 23% is hydro, and then you have 26 being natural gas, and then 22 from the wind.
That's cheap stuff then, if you look. You got a fair amount of natural sources, but Japan, the Philippines, a lot of places internal to the continent of Eurasia, they don't have much natural sources. They don't have wind power. They don't have, and they pay the price for power. Now, fortunately nowadays, there's more and more research going into what are called energy scavenging things, and really solar power. Even in some of the places you wouldn't think it's possible, you can recover a fair amount of power from the sun if you're willing to put the initial investment into that. But I'll tell you right now, coal is so cheap. It's very hard to beat the price of coal for making power. And you know, if you have water, I mean, dams are the cheapest source. If you're willing to put the money up to build a dam, I mean, Niagara Falls, where I'm from, it powers a good chunk of New York State and Pennsylvania. It's just one large power source right there at Niagara Falls. At large dams that have an enormous throughput of water, where there's a big difference in the actual levels, you know, you can get unreal amounts of power. You know, that Three Gorges Dam in China, I think it's, or Seven Gorges Dam, whatever it's called.
Three Gorges Dam.
Three Gorges, they have a phenomenal amount of power. It's like 10 or 15 Niagara Falls. That's fantastic. Another thing they're doing, I heard this from a friend named Tom Birch over in Mechanical. Listen, if you guys got to go, I don't mean to be just taking up your time, but I'm sort of goofing off right now. But in my friend Tom Birch is part of Engineers
Without Borders.
Without Borders. Yeah, you know this one? He's a really, do you know Tom, by the way, Dr. Birch?
Yeah, I've had him for his class, or I have his class this semester.
Engineers, tell him pardon me?
What class does he teach?
Intro to thermofluid, to thermofluid transport and heat transfer. It's all one terrible class.
We have to take
Not
that.
terrible. Birch is a good teacher.
Oh, he's a great teacher, but it's just so much, it's a lot of material.
You need to get into the military one time when they decide to like in the military, you cannot complain. I don't know if you realize this, but and I was on the Eisenhower. It's an aircraft carrier. I was consultant for all branches of the military except the Marines, and and they will take what we're doing in 10 weeks or 15 weeks, and they'll condense it down to like literally 2 weeks. I mean, and you don't have an option not to do it. If you don't perform, you're going to be in field artillery wishing you were dead or something. I mean, you really have a lot of pressure on you. But these guys, I tell you one thing, Navy SEALs, Army Rangers, Marine Recon, when they get, they glean off like Army Rangers, the cream of the crop, and they turn them into something called Green Berets. I don't know if you know what a Green Beret. They're infiltration people. They have to have multi-language skills. And they also, some of these people are very versed in highly technical things. Like what we're covering here, they have to know if they have to do demolitions or any kind of infiltration of systems. So they can go through what we're doing in 15 weeks in about a week and a half to 2 weeks. And I mean everything. And along with fluids and along with like basic hydraulics. And these guys can't say, oh, I don't feel like, I mean, there's nothing that they can do but what they're told. And if they don't do it, they're going to wish they're dead. I don't know how they get these guys really to sign up for this stuff because they're not paid their worth.
And it kind of drains them for the rest of their life too.
You know, this is the wild thing. If you look at the trajectory of SEAL officers, I have a couple of good friends that are both Army and Navy officers in Special Forces. They do phenomenally well the rest of their career. I'm not kidding. One of them, several of these people, I mean, they either start companies like some of these companies, Blackwater and stuff. Some of them are out in private industry. All of them they're the cream. They come to the very top in their respective careers. One of them I know ended up being a full captain. That's like an Army colonel. His name was Ricky Morris. I remember this guy. Another friend of mine, he's working, I'm not even sure what he's doing anymore. He's in an ultra classified world. But we published some papers together. He got a PhD here. And he got his master's from MIT, his bachelor's from West Point. Super bright kid. The other guy was a Navy SEAL, Ricky Morris. He's got stories. But all these guys are extremely, extremely exceptional with their determination and drive, as well as their intelligence. They're unbelievably bright. I've never realized how bright these guys were until you have to work with them. I used to think that athletes, and I played sports in high school, that athletes generally, lazy. They're never going to make it academically. I was so wrong.
It comes down to organization. Like I've had a few buddies who are in the military, and it's just kind of shocking. Like they'll share their notes with me, and you know, it's like, okay, I've got here's the voice that goes along with the lecture. This is back when I did in-person class. It's like they'd send me audio files of the entire lecture. They'd send me, you know, their notes and like a pacing thing so that like they could keep track of the online notes with the lecture and as they're writing. It's insane.
I'll tell you one other thing about the military, and it really doesn't matter if it's ours or the Russians or the Chinese. They find out the very best way to do something. And if they want to learn, they'll find out the very best way to learn and retain it. They'll find out the very best way to get the best performance. Pilots in general are the extreme examples of how to think under pressure. They're usually the brightest. You won't find this out there on the internet, but if you look at the average IQs and the performance these guys do, they're off the charts. And when I say pilots, I don't mean pilots that are cargo pilots. I'm talking about fighter pilots, long-range bomber pilots. They're unreal. And when I was on the Eisenhower, we ate with the Pukin Dogs and Grim Reapers. And these are flight groups. And I worked with some guys at Eglin Air Force Base. One guy was a pilot, and I published with them. They are super sharp guys. And they don't miss a thing, but they're trained how to think properly, if that makes sense. They catch everything. You give them one lecture, you won't have to give them a second. They'll get it. And it blows me away because some of these guys, they teach how to, I don't know if you know this, but they spend tons of money and time figuring out the best way it is to teach people in the shortest time. It can be anything, language, you pick it out, how to analytically think, how to learn chess. And they train these people. They find the best way to train them for long-term memory. And you remember what I told you early on, 50 minutes, take a 5-10 minute break, go 50 minutes. That's about what the military does for analytic thought and stuff like this. They have, you know, the funny thing is I have a good friend down here who's Special Forces, Green Beret, which is an infiltrator. So he's language specialist as well as other things. These are the guys that can come into a course that are from a major like chemistry. They can come into this course and they don't even blink and make 10s on everything. They literally blow it away because they've already been taught how to learn, how to think, and what to retain, what to ask, and they're extremely good at it. Sometimes it's scary because you're wondering, I mean, what if this guy decides he's mad at me? I mean, he could take my house down. Who knows what he could do to me? Which is another thing, because these guys, I don't know how much you know about people like this, but I had one guy I knew, he wasn't a real close friend, was a sniper. And this guy had this suit, this camouflage suit called a ghillie suit. And he got dropped into South America for an assassination on something. He can't get into any of the details. So they drop him in, he's there for 3 days and he has an extraction point, or 4 days, whatever it was. So I wait. Then when the person comes up, he does whatever he thinks necessary to get a shot, kill him. And then the only thing he does at that point, he lets whoever it is to know and runs to the extraction point, he's gone. And he said, you know, things like that sound easy until you try to do them and everything goes wrong. And you got people that spot you and, you know, your communication device doesn't work or whatever, the million and a half things. And then you got to get out of there and talk about thinking under pressure. Anyway, he had a lot of interesting stories about how nothing in life is hard after that. And one friend that my brother had who was a SEAL said that, I think my brother's complaining about something. He was working a project and this Navy SEAL guy, he's always smiling too. He told him, he goes, listen, Mark, any day I'm not cold, wet, tired, and hungry is a good day. Because that's all these guys do is suffer when they're training. Anyway, that's it. Any other questions or anything for the good of the group?
I had one question. So this is more about this is vaguely related to what we're doing. So are you aware with overclocking and the,
Yep.
you know, people who'll change voltages and all that?
You want to overclock for what? A processor?
No, this is more about one of the sources I've found. And this guy just seems to know about everything. And I can't tell what his job is.
Well, I mean,
like,
but what you mean, computers?
No, like the actual components of a circuit board, like what the price is for each module on it per 10,000 units. Like he'll know like IC, international rectifier, 00C4A, whatever. He'll know, okay, this is a smart power stage and this is how much it'll cost. And this is the price of components on this circuit board. You know, they have a huge margin on this one. There's like, you're actually giving this away. This is your leftover server components for a processor they no longer make. So it's just like he has such an in-depth knowledge of the industry that I don't know where he gets it.
Is this a personal friend or who is he?
I just found it as so I watched a channel called Gamers Nexus, and they hire this guy to do overviews of each major product release, like the whatever the latest graphics card is. They'll take the heat sink and the shroud off, and you see the PCBs.
He's probably got a lot of experience in embedded systems and building I would say this module building for different things. Anytime you get a guy that's very familiar with electronics, as well as he knows how to program in different languages and microcontrollers. That's embedded program. That's my wife does a lot of that, where he's literally creating a product that will control an old system, an analog system, from a new digital processor, and then display the information in a digital display. So he's taking the old and mating it to the new, and he has to know everything that it takes. It sounds like he's doing embedded systems, but I can't.
And from what I can, from like some of his comments, like he's got personal friends at, you know, MSI, EVGA, Gigabyte, and all of the major system integrators, where he can, like, if he spots problems with the BIOS or the, you know, whether it's reading the voltage correctly on the circuit board, and then he'll bring up those problems to those people, and he'll say, well, they got back to me, but they said they knew about it, they just didn't have time to do anything for the product launch.
You know, I don't know where he came from, but it's not uncommon for people, and he's probably being paid to do what he's doing on the internet.
Okay.
It's not uncommon for people to have a wealth of knowledge if they're doing embedded systems, everything from electrical to mechanical, all the components that are used to assemble computers. He knows all about the bus structure, the ASIC chips, everything.
Yeah.
Now, I do not do computer architecture. I don't do any of that. I know enough that if I have to, I can do something, but I don't do it. I don't need to. My work is radar, lightning sometimes, a lot of things with signal processing. And frankly, I wish I was better at what I do. That's the truth.
Yeah.
But anyway, I need to get going. It's 3:30. I do have a few things to do, but I hope I didn't hold you guys up. I know I've been yakking a little. I was hoping to get some message from somebody, but I didn't get it yet.
I'm sorry, one more thing. This is something that came back to our conversation earlier, is found a thing where it was power breakdown by state as to what the production was, and whether or not it's better for the environment to get an electric car or a hybrid.
That's a good
Like,
question.
In some states, it's like 97% of power production is coal. It's like West Virginia.
Yeah.
In Alabama, it's like a breakdown of like 15% coal, 45% nuclear, 45%, 45% nuclear, 40% natural gas.
What about hydro?
Maybe, I can't remember. I'd have to actually pull up the
It's all right.
page.
It's all right. Well, but the thing about an electric car versus a gas-powered car has to do what you're doing. If you're running around town, literally, I mean, if everything is less than a 10-mile trip on average, an electric car is perfect.
Yeah.
But I mean, if you're doing 50 to 100-mile gigs or 170-mile gigs, you got to have gas. You need a hybrid at the minimal. And then when it comes to the cost per mile, that's Jessica's bailiwick. That isn't mine, because now you got to figure out how much it costs to build the car totally. And it's always how much money it costs to do your job per year, I think. That's the way everybody looks at it in the business world. Cost per year to do what you do. And you want to minimize that without sacrificing performance. Usually, though, if you're in town and short, electric's the way to go, usually. There are exceptions, but.
This is more dealing with the environmental impact of, so the environmental impact of the greenhouse gases produced by your state electricity versus the damage produced by burning gasoline.
But that's the funny thing is this. If you're going to burn fossil fuels, it doesn't matter if it's gas, oil, coal, in terms of the amount of carbon dioxide that's created from it. It really doesn't. It just doesn't. So if you're talking about a vehicle that's going to run on gas or electricity, to get the electricity, if they're going to burn coal, then it's a wash. It doesn't matter if it's an electric or if it's a gas car. It's not you're not going to reduce that. And by the way, I got to tell you one other thing. and you can look this up. Now, here in the United States of America, we are inundated with all sorts of stuff about global warming and climate change and all that. Well, you can do some fishing online, but you're going to see there's a huge amount of scientists that say that is ridiculous for a lot of reasons. Now, I want to tell you something. In the Western world, that's what we believe according to the news. It's not really true. If you go to Asia and other places, my wife's Chinese, they laugh at that. You know why? Because they can take a look at the temperature of the earth for the last, I don't know how many thousands of years. And if you look, if you look, do you have any Asian friends?
Yeah.
That are engineers? Okay. If they came out of a good school over in Asia, it doesn't matter if they're Indian or whatever, then they know this probably better than most. Let me just see if I can get this. I'll show you something. Now we're off record now, aren't we? We're not recording.
You're still recording.
Could you unrecord it?